So today we're going to learn the binomial theorem, and it's based on what we know of Pascal's triangle. So I want to start by just doing a quick review of Pascal's triangle. I'm assuming you're familiar with the triangle, but there's some important things that I want to highlight to you because we're going to make use of them. So it's this idea of how the rows are numbered. So we start at row 0. And each subsequent row goes up by 1, obviously. And then we have this idea of row and position number. And we're going to make use of this idea. So we want to make sure that we're referencing correctly. So if I were to highlight, for example, this particular value here, 3, then that value right there is referenced as, we'll just call the value itself t subscript 3, 2, where the 3 corresponds, the 3 corresponds to the row number and the 2 corresponds to the position number. So if you count down, you see that we are in row 3 and it is in the second position. Okay. The other thing I want to highlight to you is that even though this is row 3, there are 4 items in it. So it has 4 terms in the row. And you'll see that that pattern continues. If you look at row 4, there's 5 values in that row. Row 5 has 6 values in the row. So we're going to build on that knowledge. So the first thing I want you to do is expand this term, this expression that I've given you here, x minus 2 cubed. And just so that we're all clear, so that we're all clear, when I say expand, I mean that I want you to take each of these terms and multiply everything together, collect your like terms, and give me the final expression of that expansion. So take a minute now and do that. So the answer that you should get from expanding this thing is x cubed minus 6x squared plus 12x minus 8. And you should also recognize that if I were to ask you instead to expand x minus 2 to the power of 4 or x minus 2 to the power of 5, this becomes a very long, tedious process. So the binomial theorem helps us to do this expansion a lot quicker. So here's the binomial theorem with all kinds of lovely notation, and it builds on the combinations that we were doing. It builds on the Pascal's triangle, and I'll show you how that's true in a second. And it helps us to expand these binomials much quicker. It does require some diligence on your part in terms of how you set the thing up properly. So just pay attention as we go through this, and when I show you notation or if I show you how to set up your terms, it is important. So the first thing I want to do is I want to tie this to Pascal's triangle. So we know that Pascal's triangle looks like this. And we also know that Pascal's triangle has lots of properties, lots of fun properties, but this term here, 2, for example, can be found by adding these 2 values here. This value 3 can be found by adding these 2 values here, and so on. So we can expand this triangle out indefinitely. We know the pattern, and so it makes it very easy to expand. So now what I want to do is tie that to what Pascal's triangle, or tie that to what we learned with combinations. So starting at this second row here, what I want you to notice is that, row 1, I want you to notice that the values in the row correspond to these values of combinations. And the second row would just be 2, choose 0, 2, choose 1, 2, choose 2, and so on. 3, choose 0, 3, choose 1, 3, choose 2, 3, choose 3. Okay, and if you don't believe me, test these values out on your calculator, but you'll see that in fact it gives us the values of Pascal's triangle, where the number on top, this 3 corresponds to the row, and this 0 corresponds to the position, or the term, if you will. And we have, sorry, it doesn't correspond to the term, but there are 4 values here, and there are 4 terms in the row. Okay, so I want to use the binomial theorem, and I want to expand out x minus 2 to the power of 6. And you can see here that we are given, a pattern to follow, starting at the top here with n choose 0 and ending with n choose n. So we're doing all of the terms, and then the first value uses a to the power of n, and I like to expand this term out a little bit just so that people can truly see it. So it's going to look like this: n choose 0, where n corresponds to the degree. So it's a to the power of n, b to the power of, since it's n choose 0 for the first term, it'll be b to the power of 0. So if it was n choose r, it would be a to the power of n, b to the power of r. And then the next term is n choose 1, a to the power of 1, a to the power of n, b to the power of 1, and so on. And let me just erase this. All right, this is a to the power of n minus 1. It's hard to do very fine writing with these things. And then it continues all the way to the end, where the last term, which is this one here in the pattern, is n choose n, a to the power of 0, b to the power of n. So we're going to make use of that pattern to expand this thing out. I just want you to see the pattern first. So it's starting with a. We start at the highest value of n, and then we go down by 1 all the way until we get to 0. With b, we start at 0 and we add. So it goes up by 1 all the way to n. Okay, so a is decreasing, b is increasing. Okay, so let's use that now to actually do this expansion. So what helps, I think, is if you first take a look at your binomial and you say, okay, well then a in this case is going to be x, and b is going to be negative 2. Because if you look at the pattern there, it's plus whatever b is, and in this case b is negative 2. So I'm just going to do this expansion down here. So starting with the first term, the degree is a degree of 6, so it'll be 6 choose 0, that's our first term. And then whatever a is and whatever b is, so a in this case is x, and b is negative 2. And yes, the brackets are important, so I want you to do them. And then we raise the first term, our a value, to whatever n was. In this case it was 6. And we raise the b value, which is negative 2, to the power of 0. Okay, that's our first term. Okay, and we do our second term. So it's going to be 6 choose 1, x, negative 2. And now x is going to be to the power of 5, and negative 2 is going to be to the power of 1. Okay, continuing, 6 choose 2, x to the power of 4, negative 2 to the power of 2. Okay, 6 choose 3, x to the power of 3, and I can hear you saying, why do these brackets matter? And they absolutely do, so keep them in. Okay, 6 choose 4, x to the power of, I'm going down, so that's 2, negative 2, I'm going up, so that's 4. 6 choose 5, x to the power of 1, negative 2 to the power of 5. I've run out of room. Okay, and then our last term, which is 6 choose 6, x to the power, sorry, there's the brackets of 0, negative 2 to the power of 6. Now, I know that looks like a lot of work. Trust me, this is going to help you in the long run. What you're supposed to notice at this point is that you have a total of 7 terms. If you look at Pascal's triangle, row 6 has in fact 7 terms. And the row 6 of Pascal's triangle has the following values: 1, 6, 15, 20, 15, 6, and 1. Okay? So these values here correspond to these values for Pascal's triangle. So that makes it a lot easier for us to start expanding out. Okay? Now, we have to keep going to simplify this thing. So we know that 6 choose 1 is just going to be 1, because it's that value of Pascal's triangle. Then we have x to the power of 6, and we have negative 2 to the power of 0, which is just 1. So there's our first term. The next term is 6 choose 1, which corresponds to this. And then we have x to the power of 5, and we have negative 2 to the power of 1, which is just negative 2. So that means that this expression has to be further simplified. Okay, then we have 15, x to the power of 4, and negative 2 to the power of 2, which is just 4. 20, x to the power of 6, 5, 4, so now we're on 3, times negative 2 to the power of 3, which is negative 8, plus 15 times x squared times negative 2 to the power of 4, which is 16, plus 6 times x times negative 2 to the power of 5, which is negative 32, plus 1 times, actually x to the 0, which is just 1, so I should rub that out. It's just 1 times negative 2 to the power of 6, which is 64. So when I expand this out, I get x to the power of 6 minus 12 x to the power of 5. 15 times 4 is 60, plus 60 x to the power of 4, minus 160 x cubed, plus, oh, I don't know what 15 times 16 is. Let me get my trusty calculator out. 15 times 16, I get 240 x squared, minus 192x plus 64. Now, it looks like it was a lot of work involved, but I guarantee that if you tried to expand this the other way that we had learned, it would take you much longer than this. The important things to note are you have to note what is A, what is B, keep those brackets there, and you'll see in subsequent examples why it's so important. And then you just have to know your Pascal's triangle, which is really easy. So now that you have the pattern down, I'd like you to do the next one on your own. Again, for this one, we know that A is equal to 2x, and we know that B is equal to negative 1 over x. This is going to get tricky, and it's a degree of 9. So go ahead and try this on your own. So here's what I got, and you need to check your work and make sure that you ended up with the same thing. It's interesting to note, if you look at some of the terms here, that we have x to the, for example, x to the power of 7 and x to the power of 7 here. So there's probably opportunity to further simplify, but we have terms that two terms in this expression that have the same degree. So that's a bit of a problem, and we're going to see in the next couple of examples how we address that. Okay, so one of the things that it makes it easier to work with is if we can think about the general term of an expression as opposed to the specific term of an expression, and then we can use that general term to start to solve problems. So before we start that, I just want to highlight a couple of things here. So in this question it says, how many terms are there in the expansion of the following? We can see that we can see that there's a degree of 13 there, so we would expect there to be 14 terms when we finish expanding. And here we see that there's a degree of 20, so we would expect that there would be 21 terms when we finish expanding out. Now, down here we have the general expression, the template, if you will, that all of the terms follow. This is for the r plus 1 term, and the reason for that is I want you to think about that first term in the expression. If r was 0, it gives us not the 0th term, if you will, if that's even a word, it gives us the first term. When we do our, in previous examples, when we did 6 choose 0, that was our first term. So r is, so when we are coming up with a general term, it's always going to be for term r plus 1. So based on that, let's make use of this. Okay, so here is a term here, x squared plus 1, all to the power of 7. So we know that our a term is x squared, and we know that our b term is going to be the plus 1. And we are expecting that there will be, our n will be 7. And what we want to come up with is a general term for this expression. So using the pattern that we had in the previous page, if t is r plus 1, then the general term is going to be 7, choose r, and then here's our a, and it'll be 7 minus r. So we know for that first term it would be 7 minus 0. And then here's our b term, and it starts with r. So that is our general expression, and that's very nice, but how does that help us? Well, what if the question is find the fifth term? And I'll just give you a little bit of a warning. This kind of a question was on the final IB exam. So if we're looking for the fifth term, then we're talking about r being 4, right? So term 5, which is our r plus 1, is going to be equal to 7, choose r, which is 4, x squared, and then it's 7 minus r, so 7 minus 4, which is 3, and then 1, and that's whatever r is, which in this case is 4. So that means that the fifth term, when we expand all this out, will be 35x to the power of 6. So it allows you to find specific terms. And again, this was an exam question. Okay, so now in this question it's asking us find the general term, find the term that contains x to the power of 6, the constant term, and the coefficient, which is just the number in front of the x squared term. So let's do this. Okay, so we have a, which is our x, and we have b, which is minus 3 over x squared. So that's going to be problematic. And we know that it is that our n is 9. Okay, so we are expecting to have 10 terms. All right. So, question A, the general term. So, t of r plus 1 is going to be equal to 9, choose r, x, and x is going to be, let me just erase that, give myself a bit more room. X is going to be to the power of 9 minus r, and then we have negative 3 over x squared, and that's going to be the power of r. So we need to clean this up a bit. So we have 9, choose r. And the reason we need to clean it up is, if you look at the next question where it says the term containing x to the power of 6, well, we have x terms in both a and b, so we have to clean this up and expand it so that we get our everything that has x to the power of 6 in it in one term. So since we are multiplying here, right, this is multiplication, I can rearrange this, if you will, or treat it as a great big division question. So this is like x to the power of, I'll write it out here so you can see, x to the power of 9 minus r, and that's all over x squared, right, times negative 3. Oh, sorry, it's negative 3 to the power of r, and this is x to the power of 2r. Sorry, I almost missed the r there. Okay, and then we can see that this will simplify. So here's my 9, choose r. This will simplify just using power rules. So we have our x to the power of 9 minus r, and when we're dividing, we subtract exponents, so that's 2r times negative 3 to the power of r. Okay, so you can see that we've got all the x's out of into one term, and so now we can just simplify that. I'm running out of space here, so I'm just going to simplify this whole thing to 9 minus 3r. Okay, and then negative 3 to the power of r. So that's our general expression for the term. Now, I'm going to use this in subsequent questions. So what I want you to notice is this will be how we find the exponent for the x term. All right. So I'm just going to write that general expression up here out of our way. So 9, choose r, and I'll put the constant in front, and then I have x to the power of 9 minus 3r. Okay? So then question B says, find the term containing x to the power of 6. So that means that we can just take the 9 minus 3r and say, okay, well then it would be the one that will be equal to 6. So rearranging gives us r equals 1. So that means it has to be term 2, right? Because it's term r plus 1. So it'll be term 2, which is going to be equal to 9 choose 1, negative 3 to the power of 1, and x to the power of 6. Okay, and I probably shouldn't have rearranged the negative 3 and the x, because this is in fact my b and this is my a. But anyway, so this, when we expand this out, we get 9 choose 1, and then we multiply that by negative 3, so we get negative 27 x to the power of 6. So it's term 2, and that is in fact what the term is. Okay? The next question says the constant term, the term containing x to the power of 0. So we do the exact same thing, except this time it's going to be equal to 0. So we get 3r equals 9 and r equals 3. So again, it's t r plus 1, so we're talking about term 4. And it's going to be 9, choose 3, x to the power of, what did we say the pattern was? The pattern is x to the power of n minus, sorry, so it was x to the power of 9 minus 3 times r being 3, that's 9 minus 9, so it's 0, which is what we were expecting, and then negative 3 times r, which is, which is 3. So this simplifies out to, this is 84 times x to the power of 0, which is just 1, times negative 27. And so our final answer is negative 2268. And that's our constant term, the term at the end. Okay, so now we're looking at question D, the coefficient of the term containing x squared. So again, we have our 9 minus 3r, and that would have to be equal to 2. So when we rearrange and solve, we get this answer, which doesn't make any sense. R needs to be a whole number. It's 7/3 of a number. It doesn't make sense. So what we conclude is, therefore, there's no term. Oh, my stylus is giving me a hard time. No term has an x squared as its value, and that's entirely possible. Okay. So with this next question, we have to first expand the binomial with the other binomial. Sorry, my pen isn't working for me here. So the first thing we want to do is, so it's this idea of just multiplying through, but we're not multiplying into the brackets. So what we want to do is just acknowledge that there's some multiplication that's going to be happening there. Oh, sorry, there's the 2. Okay, so we're just recognizing that there will be some expanding going on there. But what we have is this binomial that needs to be expanded and this binomial that needs to be expanded. So we just take them one at a time. Okay, so same idea, 5 choose 0 times x to the power of 5 times 1 over x to the power of 0, and so on. So 5 choose 1 x to the power of 4, sorry, whoops, sorry, that should be in there, times 1 over x to the power of 1. Okay, and you can imagine that pattern continuing. Okay, and then to that we're going to add 2 times the exact same thing. Okay. From there, you would just expand it out, just as we've been doing all along, what your final answer should look like. So I want you to try this on your own, and then I will capture the final answer here for you, and you can check your work. But you really should do this on your own first, so pause the video. So once you've completed your expansion, your final answer should look like this. If it doesn't, then you need to go back and check your work. But that's what it should look like. Okay, so with this next one, we have 2 binomials, both that need to be expanded, and it's, there's a long, tedious process involved in this because they're both, very high exponents. But basically what we're being asked to do is find the first 3 terms in the expansion. So just so that we're clear, so what we're doing is, sorry, my pen's not working. So we approach the expansion in the same way. So there's our 5 choose 0. So there's our 5 choose 0. And then x to the power of 5. And I'm going to save some space here. You know that the b is 1, so it's 1 to the power of 0, or just 1. So then the next one is 5 choose 1 times x to the power of 4 times 1 to the power of 1 plus, where are we at here? 5 choose 2 x to the power of 3 and 1 to the power of 2. And we're only interested in the first 3 terms. Okay, so then the second one is 6 choose 0 x to the power of 6, and then it's negative 2 to the power of 0, 6 choose 1 x to the power of 5, negative 2 to the power of 1, plus 6 choose 2 x to the power of 4, negative 2, oh, I'm just going to fit it in here, to the power of 2, and so on. Right? Both of these, you know that we're continuing the pattern. So I'm just showing you the first few terms of it. So let's expand it out here. We've got, as our first, for the first line there, for the x plus 1 to the power of 5, we have, once you do the expanding, okay, I seem to be having trouble with my pen, so I've written it out here. So I've just done the first few expansions, just so you can see where we're going with this. And then we know that what we have to do now that we've expanded it all out, of course, is we have to multiply everything through. And again, just remembering what our goal is, we're looking for the first three terms in the expansion. So I'm going to be taking, this would be just like any other expansion that we're doing. We're going to be multiplying each of the terms together. So that would give me 11 to the power, or x to the power of 11, minus, because now I'm going to take x to the power of 5 and multiply it by the next term, so that next value there. So minus 12x to the power of 10. And then just continuing on along, plus 60x to the power of 9, and then continuing the pattern. Okay, and then picking up from where I left off, so assuming we've done all of the x to the power of 5, then we move to the next term, so 5x to the power of 4 times x to the power of 6, which is going to give me plus 5 plus 5x to the power of 10. And notice I'm lining up the degrees of the powers underneath each other. Okay, 5x to the power of 4 times negative 12x to the power of 5 is negative 60x to the power of 9. And then 5x to the power of 4 times 60x to the power of 4, which is 300x to the power of 8. And we would just continue on with that pattern. And then the next term, 10x cubed times x to the power of 6, which is going to give me 10x to the power of 9. Okay, so again I'm lining it up. 10x cubed times negative 12x to the power of 5 is negative 120x to the power of 8. 10x cubed times 60x to the power of 4 is 600x to the power of 7. And then we would continue. And again, remembering we're only interested in the first three terms. So now that everything has lined up nicely, we can just add these things together. So I've got x to the power of 11, and I've got negative 7x to the power of 10, and then I've got 10 to the power of 9, x to the power of 9, and I've got 180 x to the power of 8, and so on. But these are the first three terms, and these are the ones that we're interested in. Okay, so that's how you would approach a question like that. Okay, so with this one we have two binomials that need to be expanded. So here's my first binomial and here's my second binomial. And what I want to do is come up with a general expression for each of those binomials. So remembering t subscript r plus 1, so the general expression for the first one is going to be, it's a degree of 8, so 8, choose r, times x squared to the power of 8 minus r, and then times negative 1 to the power of r. Okay, so that's my first general expression for the first binomial. And then we want to come up with a second one, so we'll call this t of s plus 1. The s looks a heck of a lot like a 5, so maybe put a little line through it. So t of s plus 1, and that one is a binomial of degree 7, so 7, choose r. The a is x to the power of 7 minus r, and the b is negative or positive 2 r. So we have two general expressions there that we can use. And we want to just expand them out a little bit here. So this one will be 8 choose R, 8 choose R, x to the 16, 16, oh come on, 16 minus 2R, and then we have negative 1 to R to the power of R. Okay, and this one here, we have 7 choose R, x to the 7 minus R, and 2 to the R times 2 to the R. Okay, so these are our two general expressions. And it says, in the expansion, find the term containing x to the power of 8. So we need to expand all of this out, and what we can do, because we know we're going to have to anyway, is take these two general expressions and multiply them together. So what we're looking for is 8 choose R times 7 choose R times, I'm going to put the numbers first, I think it will be easier. So negative 1 choose R times 2, or sorry, times 2 to the power of R, times x to the power of 16 minus 2R, times x to the 7 minus R. Okay? So what we're looking for is a general expression for the expansion of this whole thing. This can simplify out. So we have 8 choose R times 7 choose R times negative 1 to the R. Actually, that's not right. To the R times 2 to the R, and then our x term is going to simplify to 16 minus 2x plus 7 minus R, so that's 23 minus 3R. Okay, so, or sorry, that shouldn't be an R. I was doing R plus 1 and S plus 1. So I need to change this just so we don't mix up our terms. So just give me half a second. I'll show you what I'm talking about. This shouldn't be an R. This should be an S. This should be an S. And this should be an S. Okay, my apologies. So 2 and that one. Okay, so I need to correct that because these are two different expressions. So this is going to be an S, 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 and S. Okay, and so and I have one more correction over here and this. Okay, so 7 choose S, 2 to the power of S, and so it becomes 23 minus 2R minus S. Okay, so now we have a general expression for what we're looking for, and we can use that now to solve. So it says find the term containing x to the power of 8. So what we know then is that 23 minus 2R minus S has to be equal to 8. Okay, that's what we're working from. All right, now just give me a second, we'll go to a new page. Okay, so this is our expression because we're looking for the term that has an exponent of 8. And we can simplify this a little bit. This turns into 15 equal to 2R plus S. Okay, so that's as far as we can go from there. So then how do we solve for this? Well, we know that that R will go between 0 and 8, right? Because it's a degree of 8. and we know that s will go somewhere between 0 and 7. Okay, so what we're looking for is combinations of r and s that will add up to 15, right, to this value here. So we just want to find any combinations that will work. So let's try the first one. Here's if r is equal to 4, for example, in this equation up here, then that would mean 2 times r is 8, so then s would have to be equal to 7, because 8 and 7 is 15. So I have that combination. Okay, if r was equal to 5, then s would have to be equal to 5, and that would give me 15. If r was equal to 6, then s would be equal to 3, and that would also give me 15. And then the last one, if r is equal to 7, then s would be equal to 1, and that would give me 15. So I have 4 possibilities here that are going to add up to 15 and satisfy this equation here that will give us the exponent of 8. Okay, so now we need to solve for each of those values and come up with our final answer. So just give me a sec. Okay, so here's the 4 combinations that we have, and what we need to do now is just solve for the exponent. So for this first combination where r is 4 and s is 7, we're going to end up with 8, choose 4, 7, choose 7, negative 1 times 4, 2 times 7, and x will be x to the power of 8. And that will give us an answer of 8,960 x to the power of 8. And then we do the same thing for each of these. And I'm running out of space here, so I'll just give you the answers. So the next one is negative 37,632 x to the power of 8. The next one is 7,840 x to the power of 8. And the last one is negative 112 x to the power of 8. And then we just simply add them all up. We get negative 20,944 x to the power of 8. And that's our answer. That will be the term that contains x to the power of 8. So that's the end of the lesson. You should be able to do your homework now, and you can go back and replay any of this if it doesn't make any sense, or if you need to do some additional review.